send her the hardcover as a gift, and hope that you'll take it into her side.
Hello everyone, this is József Nagy here, and in this video you will learn the importance of grid convergence. Here you see the finished results of this tutorial, the velocity magnitude, the pressure and the temperature in the geometry, and on the right hand side you see three diagrams where I show you the importance of grid convergence, and here you see how the results change with the refinement of the mesh. The goals of this tutorial are the following. I want you to understand the set fields utility, how you define regions and how you change the values in the dictionary. I want to refine the mesh with block mesh. And I also want to simulate 7 milliseconds of the flow in a one-dimensional shock tube. And in the end I want to post-process the results. For this we will use the sonic foam solver. The official description is that it is a transient solver for transonic, supersonic, laminar or turbulent flow for compressible gas. So it is compressible, transient, laminar and turbulent. It is a single phase solver and it is a non-isothermal solver. So this means that we will have an energy equation, a certain kind of energy equation, and from that energy the solver calculates the temperature. And over the ideal gas law, we will calculate the relationship between density and pressure. Let's just jump into the simulations. And my installation is in my home. So I go into the tutorial folder, into compressible and sonic foam, and our tutorial is in laminar. And I just delete this because we do not need that. And now here is the case that is coming with OpenFOAM, and as I already told you that it is a good idea to have a base case that you can fall back on if you make a mistake. So this is what I'm going to do, but I'm not going to do it here in the Nautilus, but rather in the terminal, because you should learn how to use the terminal. I hope that by now you know how to navigate in the terminal. Tutorial, compressible, sonic foam and laminar, and here we are. We have the forward step and the shock tube tutorial, and I will make a copy of this shock tube tutorial that comes with OpenFOAM. And I will name the copied folder, shocktube underscore base case. Okay, now we have two folders, shocktube and shocktube underscore base case. I will enter shocktube underscore base case, and before I explain anything, I will open up the block mesh dictionary and change this value from 1000. And again this. So I will change this value from 1000 to 100. I will save it and go outside of the base case. And now I will make copies of this base case. 3 copies, because I want to make 3 simulations with 3 different grids. So I make the copy -r because we are copying a folder. Shocktube underscore base case, and then the copied folder should have the name 100, 1000, then the second one should have the name 1000 and 10,000. Now of course we have to change the number of cells to 1000 here and to 10,000 here, but we'll do that later on. I will immediately enter the case with 100 cells. And I want to explain you the case setup. So you see there you find the 0 folder, the constant folder and the system folder. In the 0.org folder we have the same files as in 0 at the beginning, but this is a backup folder, so if we make a mistake we can just copy our initial values to the 0 folder from here. And we will ignore these scripts, we will not use them. I enter the 0 folder where we usually have our initial conditions. We have mag-u, p, t, and u. Mag-u is the magnitude of the velocity, and these three values, p, t, and u, are important for the solver. So let me just open up the, for example, the pressure. As you see, we have the dimensions of Pascal here, and we initialize the pressure with 0. We will change this value later on. This is really a dummy file. You can consider it a dummy file. We have two boundaries called sides and called empty. On the sides, the pressure has the boundary type 0 gradient, so we are using a von Neumann boundary condition, and on the empty we're using the empty boundary condition. And as I mentioned, we are doing one-dimensional simulations here, so these boundaries define the directions in which the equations should not be solved, very similar to the two-dimensional cases that we did in the previous tutorials. So we have also a temperature, because we are working with a compressible solver. Here you see that Kelvin. Then we initialize the temperature with 1 Kelvin. We will change that to a physical value later on. And again, on the boundaries we have, on the sides have a type of 0 gradient, and empty is empty. And now maybe also the velocity. The velocity is initialized with 0, 0, 0, and again 0 gradient and empty. Oops. This I will enter here, and as you see here, you really have these dummy files, and these are the backup files, and we can copy them if we make a mistake or if we need them. Good, then I go into constant. Here you see the polymesh folder and two dictionaries. In the thermophysical properties, you can set the thermophysical properties of your fluid, like the specific heat, for example, or the Prandtl number. And here you see, for example, for the equation of state, we are using the perfect gas model, which is the ideal gas law. Okay, and in the turbulence properties, we are assuming a laminar flow. So I will now enter the polymesh folder, and here we don't see the mesh files yet. We will create them a little bit later, but I want to open up the block mesh dictionary, and I want to explain you a little bit the geometry that we are using. Convert to meters is 1, and then you see 8 vertices. And we have one single block, and this one single block is made up by these 8 vertices. You see, vertex number 0, 1, 2, 3, 4, 5, 6, 7. And if you take a look at the coordinates, the geometry is going from -5 in the x direction till +5, and in the y direction the geometry is going from -1 to +1, and the same is true in the z direction, where the geometry is going from -1 to +1. And we are using, for this case, 100 cells in the x direction and 1 cell in the y direction, and again 1 cell in the z direction. The reason for that is we only want to solve the equations in the x direction and not in the y and the z direction, and this we set with the boundaries. Here, these 4 faces of our block define the directions in which the equations should not be solved, and the sides have a type patch, and empty has a type empty. And we are using the simple grading 1, 1, 1, so we will have a uniform mesh. Good. Before I show you the geometry, I want to go into system, and I want to shortly show you these 3 dictionaries, and I want to talk about these a little bit later on. So let's just open control dict. So we are starting from 0, from the time 0, and the simulation will run until 7 milliseconds. We use a delta t of 10 to the -5. And for write control we set runtime, and which means that we will write after 1 millisecond, after 2, 3, 4, 5, 6, 7 milliseconds. Okay, as for the discretization schemes, we will use these discretization schemes. As you see here, we are using the first order upwind scheme. We will leave that. We could change it, but we will leave the standard values, and we will leave the standard values here also for the matrix solvers and the tolerances, and also the number of inner and outer loops. So now what I will do, I will create the mesh with block mesh, and I want to show you the mesh immediately. For that I create the dummy file with the extension .foam. I will save that. Now you see that here we have this dummy file, and I will immediately copy that into the other folders to 1000. Oops, of course I want to copy the foam.foam. Now it works, and also in the 10,000 folder, and also in the base case folder. Very good. Now I want to open up our case by typing in paraview space foam.foam. You can call it also shocktube.foam. Doesn't really matter. Important is that there is the .foam extension. Let's just wait till paraview loads, and if you don't know, this and sign is here, so paraview can run in the background and I can type in the terminal. Meanwhile, paraview is running. Otherwise, paraview would load and I could not type into the terminal. Okay, here we have paraview. I apply it, and here we have the geometry. So it is one block with 100 cells in the X direction and one cell in the Z and in the Y direction. If I show you the empty boundaries, these are these four faces here, and these define the directions in which the equation should not be solved. So this is the the Z and the Y direction. The Z and the Y direction. And the sides, which we set to be zero gradient in all the files, P, T, and U, these are the boundaries. I go back to the mesh, apply. Now I want to talk about set fields. Here set fields dictionary. And with this utility you can set certain fields, and this goes like this. You can set the default values and specific regions. Now what are we doing here? With the default values we will set all the cells to a certain value. So for example, with this we would set the velocity to be 0, 0, 0 in all the cells. This was also already done within the dummy file, but in the dummy files for the temperature we used a temperature of 1 Kelvin, but now we will set the values in all the cells to 348.432 and the pressure to 100,000. And then in a certain region we will change these values, but for now I will uncomment the line of the box to cell, so we do not have any regions. With the slashes you can uncomment an entire line. Do not uncomment this. I will save that, so we will now only set the default values, so values for all the cells. I go out of system. I already made the mesh, so I type in set fields and enter, and it says that it is setting field default values for velocity, temperature and pressure. Now let's take a look at it in the 0 folder. The temperature was 1 and now it is 348.432, and the pressure is changed to 100,000. Now I will delete this, and I want to include this box to cell, and which this does. At first, set fields will set these values for all the cells, and then it will set this, the values in a certain region which we define here to 278.746 and the pressure to 10,000. And we define here a box that is going in the x direction from 0 till +5. So if I go back to ParaView, so the geometry, the entire geometry is going from -5 to +5, -5 to +5, and this box that we define is going from here, the center, from 0 till +5, in the y direction from -1 till +1, so -1 till +1, and in the z direction from -1 till +1, so minus till +1. So this box represents the right hand side of our geometry. So, and all cells that are within this box will be used, and in those cells the values of temperature and pressure will be changed, but not in the other cells, so not on the left hand side. So let's just set the fields with these values, and now instead of only setting the default values, it is setting the default values and the region values within the given box. Now let's just take a look at the temperature here, and now it's not a uniform value but a list of values of 100 values, because we have 100 cells, and we have 50 entries with 348 and 50 entries with 278, as you see. The same is true for the pressure. We have 50 entries with 100,000 and 50 entries with 10,000. Okay, and if I go back to ParaView, I refresh, show you the pressure, and as you see, on the left hand side we have the default value of 100,000, and on the right hand side, within this box that we defined, we have a value of 10,000. Same is true for the temperature. There's a difference in temperature. And maybe before I go on, I want to mention that I prepared here a set fields dictionary, and there are different possibilities how to define regions. So we use the box to cell, where we define actually the starting point and the end point of the diagonal of the box. So the starting in the x direction and the end point in the x direction. I change these values, and here I only change the temperature and nothing else. You can change all the values as you want. And additionally to boxes, you can also use a sphere or a cylinder. A sphere you define by the center, the coordinates of the center of the sphere, and then the radius. So this would place a sphere into the middle of our geometry with a radius of 1. And with this cylinder, for a cylinder, of course, you have to define the rotation axis of your cylinder with the starting point of this axis and the end point and the radius of your cylinder. Now this cylinder would be located, for example, for this case, at the x of 4, and the axis would go from -2 till +2. I could have also put -1 and +1, it doesn't really matter. It takes all the cells that are within the cylinder, and I set the value to 600. But play around with this. I would suggest that you make a 3-dimensional mesh instead of this 1-dimensional mesh. So put some 10 cells in in the Z and the Y direction, and also change the empty values in the constant polymesh and blockmesh dictionary, and also in the 0t, 0p and 0u folder, and take a look at your results. I just wanted to mention that you can also use different shapes, not only boxes. But now let's go back to the shock tube tutorial. I made the mesh with blockmesh, I set the fields with set fields, and now I want to run the simulation. And the simulation finished within 2 seconds. So it was a very fast simulation. And now if I refresh the simulation, then we should, yes, we have the results. Well, what's happening here physically? So we have a geometry that is 10 meters long, and in the middle you can imagine that there is a membrane that is separating the two regions, a high pressure region with 100,000 Pascal and a low pressure region with 10,000 Pascal. And this membrane disappears at the time 0, and then the high pressure gas is creating a compression in the low pressure gas, and actually it is creating a shock wave within the low pressure gas on the right hand side. And you can see the traveling of this shock wave, which you see here, to the right hand side, and on the left hand side the originally high pressure gas is expanding. Now, and physically this shock wave is a discontinuity in the field values, in the pressure and the temperature and the velocity. But if I show you the values along a line in the center of our geometry, we'll only use 100 points. This is the pressure here. If I go back, here you see this discontinuity at the beginning, and then the traveling of the pressure of the shock wave. And this should be a discontinuity, but this is not a discontinuity, that's for sure. And the reason for that is that the mesh is too coarse for this case. And if I show you here the velocity, if I zoom in, the velocity is going from 0 to 200, a little bit less than 300. And if I zoom in here, you see that this continuous jump is smeared over 1, 2, 3 and 4 cells, at least four cells. But the geometry is going from -5 to +5, so it's 10 meters long, and we have 100 cells in it. So one cell has a length of 10 centimeters. So this discontinuity is going at least over 40 centimeters, which is most definitely not a discontinuity. And this is the reason why I want to make the same simulation on different grids. I will go into the shock tube 1000 case, and I will immediately change the resolution of the mesh from 100 to 1000. I will create the block mesh. The setup is the same, and I will use the same set field settings. I made the mesh, I can set the fields, and now if I take a look at 0 temperature, instead of a list with 100 entries, I have 1000 entries into the list, with 500 entries at 348. If I go down, 500 entries, I go down, and in the end we have the boundaries. The same is true for the pressure. Okay, so now I run the simulation, because I set up the initial values and the mesh. I don't change anything in the system folder. This takes a little bit longer, but not really. simulation stopped, and I will load now this case, the 1000 cell case, the form.form with the dummy file. Now it is located in the same location. I will translate it into the negative y direction. And if I show you the mesh, you see that the mesh is so fine that we do not see anything. So I really have to zoom in here. Yeah, you see? And now I want to show you the velocity. And one cell corresponds to 10 cells here. And here in this mesh, one cell has a length of 1 centimeter. So although here the discontinuity is going over 1, 2, 3, 4, 5, at least 5 cells, but this corresponds to a length of 5 centimeters and not 30 or 40 centimeters like here. So this result is closer to a discontinuity, but I still want to show you a finer mesh result. So I go into the ShockTube 10,000 tutorial case, and I have to change the number of cells, of course, from 100 to 10,000. Okay, I make the mesh. I execute set fields. Very good. And I execute Sonic Foam. And we have an error message. Actually, the simulation diverged. Get used to these error messages. You will encounter them, especially in the beginning of your OpenFOAM career. What happened here? Here you see that the Courant number, the maximum value of the Courant number is 2.84. And if I scroll back here to the case with 1000 cells, now if you don't know what the Courant number is, or the CFL number, I pulled up the Wikipedia page here, and the Courant number is made up by the velocity even in a given cell, by your delta t, your time step, and we defined it to be 10 to the minus 5 for all the cases. So velocity delta t divided by the cell length. And usually this value should be less than 1 in most cases. And as you see here, it is not less than 1, and this is why we have this error message. The simulation just diverges. Originally, this case was set up with 1000 cells, so it works for 1000 cells, and the maximum value is less than 1. But now with 10,000 cells, I reduced this delta x by a factor of 10, and this increased the Courant number by a factor of 10, which means that now I have to reduce my time step because the velocity will be the same physical velocity value. So I reduced this value a factor of 10 in order to have more or less the same maximum value of the Courant number. And the question is, why didn't I change the delta t for 100 cells? If you go back to that case, you will see that the maximum Courant number was 0.029. So I could have increased this delta t, because what I did with 100 cells, I increased the length in comparison to the 1000 cell case. I could have increased it to 10 to the minus 4, but I didn't bother, because the simulation ran in 2 seconds. But for a complicated simulation that runs for a day or weeks, you really should take care of this Corona number, so you are as close to 1 as possible. Or you can just make OpenFOAM do that for you. Okay, so now I decreased my delta t, and now I will have a maximum Coulomb number of 0.29, like before. And now the simulation is running. This will take a while because we have more cells and we have more time steps. So I will stop the recording now, and I will also conclude this first part of the tutorial. I hope you enjoyed it, and I hope that you learned something. Thank you for watching, and I hope to see you in the second part of this tutorial.